Okay, good morning, ladies and gentlemen. This is the last session of our summer camp. And I present to you Dan Melman on machine translation.
Morning.
Morning.
Morning. It has been an exciting 6 weeks. During the course of this presentation, you might get a hint of just how exciting. This is, can't hear? Is the mic? Oh, I see. Okay, so good. So this is our team presentation, and I really mean that word team. I mean, what I'm about to present could not have been done within a huge amount of work by each and every person on this slide. So even though I'm going to be doing most of the talking, please imagine 13 people standing up here and talking in unison. Besides our actual team, we have many people to thank who have helped us to come to this point. And I might have forgotten someone. I apologize if I did. But it's actually amazing when you think about how many people helped us to do what I'm about to tell you about. So, without further ado, let me say a few words about why we came here and what we tried to do. It's fairly well known in the MT research community that state-of-the-art machine translation often produces what we call affectionately word salad. To get the words right, they tend not to get the order right in many cases. It's also fairly well known that trying to use trees as features in a finite state framework doesn't work, or doesn't seem to help. I mean, it's possible that somebody will yet discover a way to do that, but so far they haven't. Another known problem is that machine translation is very compute intensive, and a problem that I think is actually the biggest problem of them all is that these systems are getting very complicated, making them hard to study and improve. So let me say a few more words about the engineering motivation for using syntax in machine translation. Generally stated, the theory goes that you might need fewer parameters to express ordering information if you encode this information in tree structures. Fewer parameters are easier to learn for a machine learning system, given the everyday fact that we have limited training data and computing resources. So this means, first of all, that less training data should be required to reach a given level of accuracy. And the flip side of that coin is you can get better accuracy on fixed amounts of training data. So goes the theory. Taken a little further, the theory says that all parameters interact during training. So in fact, if you get one set of parameters right, they might help you to get the other parameters right as well. But there's a worry, right? That despite these theoretical advantages, in practice, using trees is just too slow. Right? I think that's a myth. The myth says that, translation involving syntax, translation models are just computationally too expensive to learn. I think the fact is that finite state models are actually more expensive to learn because they have more parameters. Right? And of course, you don't want to do both because then you incur the combined cost of both. And there's also work in machine learning that suggests that if you're doing structured inference, which is often what we do in NLP, better models should actually train faster because they spend less time looking around parts of the search space that are fairly flat and uninformative. So that's the theory for what motivated our team's work. More specifically, what we hope to accomplish with what we did this summer, not just by doing what we did this summer, but in the long term as well. Here are some points. We want to make it easier for other people in the field to do the kind of research that we want to do. We want to lower the entry barriers to the field. We want to demonstrate the feasibility of doing statistical machine translation by parsing, as we call it. I'll explain, of course, a lot more about what that is. We want to dispel some of the myths surrounding this approach and make it more attractive for people to work on. In both the short and long term, we want to answer some fundamental scientific questions that can only be answered using this approach or that pertain only to this approach. We have educational goals as well. I'll say more about that in a minute. And by lowering the entry barriers and by doing some of the other things I'll tell you about, we want to accelerate progress in MT. For reasons of these systems complexity, I think the progress of the field, although it has been impressive, I think it can be much faster still. And of course, long term, we also want to bring MT back into the fold, as it were, of mainstream NLP research. I think many of us have seen that that MT has become a subfield that has started to diverge. And personally, I want to reverse that trend. So I'll say more about these things later, but let me tell you a little about what we did. Our work was partially structured based on a previous successful example of one of these workshops. I was here in 1999 with 9 other people where we produced the Egypt toolkit, which includes Giza. Some of you may have heard of this. It's a piece of software that's cited and used by probably more than half of the MT papers published today. Along with that toolkit, we also, in 1999, we also released a visualization program that was useful for that kind of machine translation. We had 2 undergrads on our team, one of whom went on to fame and fortune right here at Johns Hopkins. I don't know if he's in the room today. And that workshop team proved the feasibility of statistical machine translation as a way of doing research in this field by showing that you can get results with that kind of system that were comparable to the best results at the time, at least on some data sets. Right, so it gave many people in the field cause for optimism that progress could be made in this way. And we see now the effects of that. Right? And indeed, in the years since 1999, a huge amount of progress has been made, particularly in this paradigm. So we were hoping to imitate this way of accelerating progress in the field. So in 2005, this summer, we released the GenPAR toolkit. GenPAR stands for Generalized Parsing. And I'll be saying many things about the connection between MT and parsing. It includes what we call sandboxes. This is one step we took beyond the Egypt toolkit, which I'll say more about later. I'll also tell you later why no separate decoder is required for this approach, which we view as a feature. We also produced a visualization software, which we call the Multi-Tree Viewer, or MTV for short. We also have 2 brilliant undergrads on our team, at least one of whom has expressed an interest in going on to graduate school in NLP. And I believe we have shown the feasibility of statistical machine translation by parsing. We'll present some evidence for that as the talk goes on. So we copied more from the 1999 team. What happened in 1999, and I speak from experience because I was there, is that we spent about 1 week, this is averaging over all the team members, right? We spent about 1 week on data preparation, about 3 weeks on software engineering, about a week on system integration, and about 1 week on research. And well, we thought it worked for them, so we did the same thing. And this presentation, our team's presentation, will follow roughly this order with roughly this proportion of time allocation. So this is actually the outline of our presentation. Okay, and a little more seriousness. I will say a little bit about data preparation. It's not trivial for these kinds of systems, well, or for any kind of SMT system, actually. I'll say a lot about our GenPar toolkit. I'll say a few things about feasibility of statistical machine translation by parsing. We will have 2 proposals for follow-on research, wherein we will show more evidence for the feasibility of statistical machine translation by parsing. And then we'll present the results of an empirical study. That's our scientific contribution, in addition to the others. Okay, so for those who haven't done this kind of thing before, I just want to quickly outline what is involved in data preparation for this kind of research. First, you obtain some corpora, and that's not as easy as you might think. Tokenize it, lemmatize it, then you look at it and you discover you haven't quite done it right, so you retokenize and you relemmatize. Then you have to adapt the text format to these external tools that we use. So it's common in syntax-directed approaches to machine translation to use biases from monolingual tools like taggers and parsers, and we have done that. So we had to integrate those tools, actually use them on a large amount of data, which also is not trivial, do the standard partitioning of data for machine learning, filter out sentence pairs that were rejected by some of these tools, induce word-to-word translation models is another bootstrapping step, filter out more sentences. And then we find that our friends who build these taggers and parsers can actually give us better tools, and so of course we want to use them. And so we repeat from step 3. So 1 week times 13 people, yeah, that's what happens. So, okay, enough of that. Let's talk about GenPar. GenPar is a toolkit for generalized parsing. We believe it is an integrated end-to-end system for translation by parsing, which is easy to obtain, i.e. you can download it now, understand, use, study, modify, extend, and improve. And we've done some of each of these things. It was intended to have a relatively simple yet general architecture, and I'll say a lot more about that. It has an intuitive, flexible, and object-oriented design. I'll say some about that as well. It has documentation. Imagine that. Many of our favorite research prototypes are usually lacking in that category, but we tried our best. Dynamically configurable, easily extendable, blah, blah, blah. Freely downloadable, that's the key point. You can go to this URL. Okay, so let me say a little more about GenPar. First, I'll say a little bit about the main challenge that this toolkit tries to address. I'll talk about a key algorithm involved. There's only one. System design and design extensions, and a few words about system integration. Here, don't worry about the details, right? This is a bird's eye view of a data flow diagram for statistical machine translation by parsing. There's a lot of stuff here. Right? If you have never done statistical machine translation by parsing, or even just statistical machine translation, and you want to get into the field, and you start thinking about the stuff you have to build to even start, this is kind of scary. And complex systems pose many challenges. Right? They're hard to study because it's hard to do controlled experiments. Right? Lots of variables. Right? How do you control variables if you don't have a system that's easy to configure? If you run an experiment and something changes for better or for worse, it's very difficult to assign credit or blame for one part of the system or another. So it's very difficult to get insights into what would make the system better. They're also often hard to modify and extend if significant effort has not been put into software engineering. And they're hard to replicate. One trend that I've noticed since people started publishing papers on SMT by parsing is that typically they will give results for their own system and a result for a system that does not use parsing. But I've yet to see any result that cites another paper's result and says, okay, we replicated this, or we did something like this, and then we improved it. Right? And this kind of improvement of one system on another is fundamental to science. And yet we have a lot of difficulty doing that in our field. So it's hard for the community to make progress. This is what I meant when I said that even though we're moving pretty fast, I think we could be moving much faster still. Okay, so what do we do to lower the entry barrier and to reduce the system complexity? What we did is we implemented this whole thing, and we implemented it in such a way that the four of the key, most difficult pieces to write are actually one piece, right? The exact same piece of code does all four of these things. And I also want to point out that 2 of the remaining processes are trivial, and for 2 of the others, you can get standard tools. So basically, we have done all the hard stuff, and we've made it simpler than you might expect to do the hard stuff. Okay, so more about generalized parsers, right? How is it possible that all 4 of the hard pieces, or what I think was the hard pieces, can be done with a single algorithm, with a single piece of code? To answer that question, I'm going to have to explain a little bit about what we call multi-trees and multi-parsing, and then I'll show you how different incarnations of this one algorithm can do all these things. So what's a multi-tree? Well, we all know what a tree is, as in a parse tree. It's a recursive structure, right? Constituents on the internal nodes, words on the leaves. A multi-tree is a structure of recursive correspondences between 2 strings. Right? So the 2 strings are at the leaves of this structure, right? And we can show the recursive correspondence with these nested rectangles. Right? So for example, this rectangle here shows that the word dishes, with its part-of-speech tag, corresponds to this word pasudu, with its part-of-speech tag. This is a simple English sentence with its transliterated Russian translation. This correspondence is nested within a slightly larger correspondence. This larger correspondence says that the noun phrase, the dishes, also corresponds to a single word because there are no determiners in Russian. And similarly for this rectangle here, that's a word-to-word correspondence. And then this largest rectangle, which encloses everything, is a sentence-to-sentence level correspondence. So you can see that these rectangles are nested. It's a nested structure. This is a 2-dimensional representation of this multi-tree. Right? I like pictures like this. I like them so much that I try to devote a significant portion of our team's effort to building a toolkit, a tool specifically for looking at multi-trees in all their incarnations. Our tool is called MTV. This is just a screenshot with its various options. Here's one perspective on multi-trees. Right, I'm going to show you the same multi-tree from 4 different views. This is a way of looking at multi-trees that is often found in papers on alignment or translation. You have one sentence on the top and its translation on the bottom. The concentric circles represent essentially X-bar levels. The arcs represent dependencies, and the vertical lines represent translational equivalents. Right. Here's another view on the exact same tree. This is the 2-dimensional representation that I personally like. Again, each cell represents translational equivalence. The arcs represent dependencies, except now dependencies on different dimensions are merged into a single line if they're actually between the same corresponding words. And again, the nesting represents X-bar levels. As you can see, this representation works equally well when parts of one side or the other are not linked to the other side. Here's another perspective on the same thing. This is just the ordinary tree representation, except that we show information separately for each of the languages. And then some people like this representation. We actually have the 2 separate trees with links drawn between them. So any way you want to look at it, it's in the tool. It can even handle head switching for displaying. Right. There's another view of the same thing. Okay, so that's the advertisement for MTV. Now I hope you understand what a multi-tree is. How do we get multi-trees? To get multi-trees, we use something called a multi-parser. If an ordinary parser uses a grammar and takes a string as an input, a multi-parser uses a transduction grammar and takes a string tuple as input. So here's our grammar, a bunch of production rules. These are what we might call two-dimensional or synchronous production rules. They indicate what happens separately in the derivation of two strings, separately but simultaneously. And here's some input. Again, that same simple English sentence with the Russian translation. And let me demonstrate how the process works. So as in ordinary parsing, we have production rules constraining the possible inferences of the parser. So suppose we have a production rule like this, which says that a pair of nouns on the left-hand side can go to these two. These are intended to be roughly part-of-speech tags. Then in our chart, we can derive this, what you can think of as a two-dimensional item. Right? And I've skipped the initialization steps of scanning. Right? Just assume we've read in the strings already. Okay, we can do the same thing for the other word-to-word correspondence. And then we can do composition like we ordinarily do in bottom-up parsing, except we're doing it in two dimensions. Right? A 2D item can combine with a 1D. Two 2D items can combine into the sentence. Right? So we're building up this recursive structure bottom-up, just like we do in ordinary parsing, except now we're doing it in two dimensions. So this is multi-parsing when you already have a grammar. One of the challenges in statistical machine translation by parsing is to get a grammar like that in the first place. And this is typically done by a process that we call, well, at least an important part of the process is something we call alignment, where you have a bunch of parallel text as training data, and you may or may not have other biases that you introduce into the process. So a typical way to proceed is to have monolingual trees, monolingual parse trees for each of the strings in the input. So then and a word-to-word translation model to map correspondences. Right? So your input might look like this, right? You have monolingual tree on one side, monolingual tree on the other side, and you have this word-to-word model that says that dishes translates to pasudu, that the usually disappears in translation, and so on. Given these kind of constraints, the parsing process proceeds exactly the same way. Right? The parsing algorithm can query whatever it is that represents these constraints in the system for permission to make inferences and for the costs of making certain inferences. Right? And these constraints, or whatever encapsulates them, returns a cost, or returns permission to make the inference, and the parser proceeds and makes those inferences and puts them in the chart and does all the standard stuff that parsers do. So word-to-word correspondences, and again, building up recursive structure. Notice that every node, right, every non-terminal node in this recursive structure is consistent with the constraints. Right? So the parser would not be able to infer an equivalence between these first two words and some other word, because this tree would not permit it. There's no constituent in this tree that would allow that. Or, in fact, that constituent would be inconsistent with this tree. So it's the same algorithm, but with different constraints. Right? Now, it turns out that translation itself is also the same algorithm with a slightly different set of constraints. The main difference, of course, is that in translation, you do not have the output string. You only have the input string. But you do have your transduction grammar. So if I've initialized my parser with the words in the input, and I gave them span information, right, and part-of-speech tags, and I've seeded my chart with the possible target vocabulary with no span information. Whoops. And I'm missing a production rule here. But if I had one, then I could make the inference that these two initialized items can compose into this 2D item, just like we did for multi-parsing and for alignment. Right, there's the missing production rule. This is the other word-to-word correspondence. Works the same way. So what I'm showing you here is complete inference rules. Given the stuff above the line, I can infer the stuff below the line. Right? And we proceed recursively. Right? So this is another initialized word on the English side. This is my production rule. I can put those together to create a larger item, just like I did with the other two examples. And again, two two-dimensional items and the relevant production rule combine to form a complete sentence. So what I've derived here, given one input string and a transduction grammar, is a multi-tree. All right, so the result of translation is a multi-tree, just like the result of any other kind of multi-parsing. But wait, you say, we don't want a multi-tree. We want a string. Right? When we're doing translation, we're interested in the target string, right? We don't want a tree. Well, that turns out to be trivial if you have the tree. Right? You just read off the leaves of the tree in the output component. And the information about the relative ordering of leaves in that tree, or constituents in that tree also, is encoded in the tree, because the tree keeps track of which production rules were used to make the inferences. And of course, on the right-hand side of production rules, you have a particular ordering of constituents. So this is what I mean when I say that no separate decoding software is required. Right? We have this multi-parser that does everything for us. It does alignment, it does multi-parsing for training, and it does the actual translation. And the ordering information is encoded in the multi-trees. So there's a single inference algorithm that you need. And in fact, we have implemented it in a single piece of code, which I think is nice because it takes less time to debug and maintain and improve and all those nice things. And this single inference algorithm just has varying constraints, whether they be production rules or pre-existing monolingual trees, or sometimes the input string on both components, sometimes not, sometimes just one. So that's sort of conceptually what we want. In practice, it might be easier said than done. So let me tell you a little bit about the design goals for GenPar, right, with a view of implementing these algorithms. We wanted it to be a system that was powerful and configurable, can instantiate many different kinds of machine translation by parsing systems. It has abstract classes that interact in a fixed but generic way, and the concrete variants can be chosen at runtime via config files, specific parsing algorithms, types of grammar, pruning strategy, what have you. We wanted it to be easy to understand, and we wanted it to be easy to extend. And as one of our undergrads pointed out, doing these three things simultaneously is hard. So let me say a little bit about the core of the design. And those of you that have worked with monolingual parsing will recognize this as being nothing new, really. This is how you might put together a monolingual parser. Right? You have the parser itself, which coordinates various other components. So it might have a non-deterministic part that generates inferences, a search strategy embodied in an agenda with a comparator. Of course, it has a grammar, and it has some input. You might have different parsing goals, right? So usually you want to infer a non-terminal that has the grammar's start symbol as its label, spanning the entire input, but you might want to do other things too. Typically, you will have a chart associated with the algorithm that stores items. And you might have various pruning strategies. You might use outside cost estimation for re-ranking the items and so on. So if this was taken out of context, you might think I was talking about an ordinary monolingual parser. The only difference is that in our case, we're talking about multi-trees instead of ordinary trees. And the input might consist of tuples of strings rather than just single strings. And the grammar is a transduction grammar, or a functional approximation thereof. So that's the core of the design. here's what the parser actually does. And again, this is very standard for monolingual parsing. Our main contribution is that we've extended it to multi-parsing. Right? You start with an empty agenda. And so the first time you go through this loop, the agenda is empty, so you don't do this. You just call the logic to expand on whatever trigger item you have, which is initially null. So the first time you go through this, the logic does its initialization based on the grammar. Then, based on the first items created, if the item is not to be pruned, according to your pruning strategy, you push it onto the agenda. Right? Of course, second time you go through and subsequently, if there are things on the agenda, then you have to pop the agenda to know what the trigger item is. And you just continue until either the agenda is exhausted or you reach your parsing goal. When you finish, the logic can output your result, which is, in our case, a multi-tree with costs. Let me say a few words about two of the key abstractions that have helped us build the system that we built. One is the idea of parsing logics. So the straightforward way to code up a parser is to just, to basically combine the inference generation process with the search strategy all in one. So you might code a CKY parser, right? It means you're generating inferences bottom up and you're looking for them left to right, or smallest span to largest span, and within that ordering left to right, for example. Right? Deterministic parser, you know exactly what's going to be considered at what point. We wanted to be a little more flexible. Right? So we abstracted this non-deterministic part, the part that generates inferences, into a separate component without saying how those inferences will be ordered on the agenda. Right? We let the agenda do the ordering. Right? So the logic does not specify the full order of compositions, but it can if it wants to. Right? So we're flexible with respect to the degree of non-determinism in the logic. As we will see, this will be important. And this is the idea partially based on work of Schieber et al. In 1995. And for example, if you wanted to code up the CKY algorithm, the way to split it up using this abstraction is you'd say, okay, the logic is bottom up, and then the search strategy is shortest span first. Right? This tells you which items can be generated. This tells you in what order they should be considered on the agenda. Given this abstraction, it becomes easy to code up alternatives. Right? So with the same bottom-up logic, I might decide that I'm going to do best first parsing instead of CKY, or left to right, or even random if I feel like it. The only change required is to write a new comparator, which is a relatively tiny piece of code and pretty easy to write. I don't have to code up a whole new parsing algorithm. Another key abstraction is grammar encapsulation. So we have a hierarchy of grammar classes, some of which contain production rules, like you would expect from a grammar. But some of them have nothing like production rules. In fact, we have one grammar class that contains two streams of trees, monolingual trees, and a stream of word-to-word alignments. But interestingly, this is all encapsulated within the grammar. When the logic queries the grammar for permission or the cost to make inferences, the logic knows nothing about this. Right? The non-deterministic algorithm that generates inferences doesn't care what kind of constraints the grammar has in it. It just wants to know a cost. Right? We have made this division, and we have benefited greatly from it because we've been able to code up all kinds of different constraints within our grammars without changing the parsing algorithm at all. So this aspect of the design and some of the other aspects have made our system, have made it surprisingly easy for us to implement variants and extensions to our work. Let me give you a few examples. So we have this hierarchy of logics, actually. We have an abstract base class. We have a bottom-up logic, which implements this expand function, if you recall from the pseudocode. It's an expand function in the logic that generates new items. It has two methods to implement that method. Scan and compose, right, the standard kinds of inferences you have in bottom-up parsing. We have specialization of it for the translation case, where we add a loading kind of inference. This is where basically we're seeding the grammar with the target vocabulary. This is one method, right? It's not that hard to write. Most of the code is reused from higher levels. And then we made it better. We wrote a faster bottom-up logic by overriding this naive loading function with one that filters the target vocabulary with words that might actually be translations of your input. Right? Otherwise, it's fairly inefficient. This was a fairly straightforward change. It took me about a day. And the result was a reduction in number of inferences required, in some cases by up to 2 orders of magnitude. So easy to make optimizations, easy to make extensions. Here's another example. Given that bottom-up translation logic, one member of our team said, well, using an agenda sometimes is too much overhead. Right? Sometimes I want to parse without an agenda. I want to have a more direct connection between my inference algorithm and the chart to save time. So this team member wrote another logic which overrides the expand method in this logic and just directly implements the entire CKY algorithm. After translation, the expand method returns an empty set, so the agenda is actually never used. Right? In that piece of pseudocode I showed you, the agenda access methods just fall through because they evaluate to false. And the logic still uses the superclass's helper methods for generating the inferences. Right? But this was a very easy way to say, OK, suppose I don't want any non-determinism. Right? I want to hardwire stuff for speed. No problem. It's easy to do. Right? So again, here's that generic algorithm. Right? If the agenda is always empty, then this loop won't happen. And if there's nothing returned, then this loop won't happen. So basically, the entire algorithm is encapsulated within this method call. Right? So our top-level parser accommodates this very straightforwardly. Right? If you don't want an agenda, no problem. OK. Another example is another kind of grammar that we implemented. We started off with a strong bias for both of the languages in the input, but then we decided, OK, well, what if you don't have a parser for both languages? Suppose you only have a parser for one. OK, well, we just implemented a new grammar class where the inferences that can be generated are constrained by just one tree on one side. The structure of the other side is unconstrained, except by the structure on the first side and the word-to-word translation links. Again, this is completely transparent to the logic. We also implemented a grammar class that uses no constraining trees, and you'll hear more about that later.
So, just a quick question. So you mean to say that the trees on the output side are isomorphic to the trees on the input side?
No, they're just absent. Right? There's no constraint.
How do you get things like word order and stuff like that?
This is just for alignment. Right? This grammar class is used just for alignment. Right, so not all classes are useful in all situations, but so the user has to understand a little bit about what they're doing when they use these, but they're there and they're easy to implement. One other thing I want to talk about, something we started doing but haven't finished, but I just want to show you how easy it is within our framework, at least conceptually. There's an interesting movement in the field these days to use what people call phrases to do machine translation. So we decided to go with the flow and see what we can do about phrases. So let's assume that we have a phrase list for one or both languages. I'm not going to say about how we get that phrase list. Lots of papers out there on that. But suppose we have a phrase list. And let's just consider the easy case of contiguous n-grams, which is essentially pretty much all that's used in current literature. We can also do trigrams, but that's a bit trickier. I'm not going to talk about that, but suppose we're just interested in phrases like the examples I have here. Kick the bucket, there is, account for. Notice that these don't need to be any sort of linguistic constituent, at least not according to any linguistic theory that I know. The solution within our approach is to treat each phrase as a possible constituent, linguistic or otherwise, with a unique non-terminal label. When you're doing alignment, you then identify each such, you attach, I'm losing myself. Attach to identify each such non-terminal with the lowest subsuming node in its constraining tree, on the monolingual tree. Right? And then you replace its sibling non-terminals with slightly modified non-terminals. Here's an example. Suppose I have the phrase AB in my phrase list, and I start with a constraining tree like this. Right? Well, then I'll say, okay, well, AB is going to be a phrase with its own label, and and this non-terminal label will simply be relabeled to remember the fact that we have removed the B from it. Okay, so you do this kind of transformation, and the monolingual projection of the resulting multi-tree will then look like this. And this phrase is in there as a constituent. Okay? Then after the alignment stage, during multi-parsing for retraining and during translation, we would just use a try for efficient phrase recognition during scanning, right? In other words, to recognize that phrases are there in the input. So use a try. Seed the chart with them, right? All we have to do is allow items whose scan span is wider than 1. And that's it. Right? The algorithm, the inference algorithm need not change at all. Right? All these changes, right, the way the relabeling is done, right, the labeling function, right, and the encapsulation of the phrase list happens inside the grammar. Right? So again, a new grammar class, you got phrases. Not too hard, we think. But we haven't done it yet, but we're going to.
So do you do EM training?
I'll get to that.
But, I mean, that might be a little trickier here.
If I'm...
And then you've got to let these separate A's and B's compete with the new OD type.
Right. So as long as you recognize them when you're scanning and they're in the chart together with the unphrased A's and B's, then they compete. Right? Yeah. So you're right. Okay. Let me say a few words about system integration. So again, don't worry about the details. This is a bird's eye view to show you sort of what we had to deal with in the system integration side of things. I remember that after my 99 team released Giza, many people complained that, well, there was no decoder, and even after you got a decoder, it took some effort to make it work together with the alignment model, together with the language model. It required a fair amount of expertise just to make the thing work. And we wanted to eliminate this barrier to potential users of our toolkit. So what we did is, well, first of all, of course, we had to have such a system here in order to do anything. And what we did is we encapsulated it within our tool. Right? We took all of these pieces, right, and created a directory structure that has one process per subdirectory. We gave it a tiny corpus as input, and we used makefiles and other mechanisms to tie it all together, so that when you download the tool and unpackage it, you get this directory structure on your machine. And with one command, after compiling, with one command, you can run through this entire system in 3 different language pairs. We hope. At least that was the aim. So we call these sandboxes, right? They're kind of a place to play with the system. And they really serve 3 valuable purposes. One is that anybody who wants to further develop our tool, ourselves included, can use it as a validation suite, right? So every time you make a change, it was sort of an edict on our team that when you make a significant change to the code, you have to run it through our sandboxes to make sure that nothing breaks. And the way we do that is that within each subdirectory, we have what's called expected files, right? A file that records the expected result of running the code through this sandbox, right? Then when you get the actual output, you compare and see if there's any differences, right? And so we were always saying to each other, has it cleared the sandbox? Has it cleared the sandbox? So this is very valuable for quality control. The sandbox can also serve as an educational tool for people who want to familiarize themselves with what's going on. It's probably the best way to do that is actually just to peek around the sandboxes, see which files are where, what goes into what process. We tried to document it as well as we could. In addition to people using it themselves, we're hoping that instructors of NLP courses or machine translation courses can actually use this and just give it to their students and try to explain how it works and so on, and have the students actually be able to learn about it quickly enough, within the span of one course or less. And it also serves as a blueprint for experimentation with this kind of system. So if I'm done learning with it and now I want to run some serious experiments, our intent is that you should be able to do a recursive copy of this directory structure into a new place and just feed it new data. And again, with one command, in theory, you should be able to run your data through the entire pipeline the same way. I mean, it'll take more time if you have more data, of course. But, right, so it's a blueprint for how to use a system like this for real. Like I said, our toolkit includes 3 such sandboxes with different configurations in each one, so you can try different things, and of course, different language pairs. How am I doing for time? 45, so I'm about halfway through.
50 minutes.
Wow. Okay, doing good. Okay, so let me say a few words about feasibility. And I'll tell you right off, we didn't shatter any world records here. That wasn't our main thrust. But let me just tell you about what we did do. In fact, our student proposers will say a lot more about it than I will. But so first of all, parameter estimation in the toolkit currently is actually very primitive. Right? This wasn't something we worked on at all, I don't think. But the idea of the design is such that, again, in theory, we haven't actually done it, but in theory, there's this abstraction called a learnable grammar, right, which needs to implement just 2 methods. You need to be able to give it a corpus and have it learn from that corpus something. And it should probably support a normalized method, because for different learning algorithms, you want to normalize at different times. We have one particular learning algorithm, which is essentially Viterbi estimation. But I think the design admits the possibility that you could plug in whatever learning algorithm you want here, have it use the parser as its inference step, like the E step in the EM algorithm, and have it update a grammar that is a subclass of this learnable grammar interface. Right? I mean, again, this is conjecture to some degree, but I believe that little or nothing would need to be changed in the toolkit to incorporate new machine learning here. Okay, so that's parameter estimation. The configuration we used for most of our experiments, again, is just first cut. We didn't actually vary too much from this because, in fact, most of our experimentation was aimed towards scaling more than getting high accuracy numbers. And the scaling was actually more on the flavor of software engineering rather than optimization. In other words, getting things correct rather than fast, for the most part. But we made good progress on that, though. So for the most part, we used a bottom-up logic. For the most part, actually entirely, we used a bottom-up logic with a best-first strategy, mostly but not entirely. The grammar for alignment was a tree-constrained multi-text grammar. For retraining and translation, we used a bilexical probabilistic MTG. The particular flavor of bilexical MTG we used had a fine-grained generative process with strong independence assumptions, but no smoothing. Okay, so this is pretty close to a straw man kind of system. Really more a feasibility demonstration. And so yeah, so that's what I wanted to say about that. Now, I want to say a few things about so the data we used. We experimented mainly with two language pairs, French to English and Arabic to English. For English, we did standard tagging and parsing using tools that were provided by Adwait Ratnaparky and Dan Bickel. Thanks very much to them. The French to English data was the Europal corpus commonly used in this field. For Arabic to English, thanks to Mona Diab for her Arabic tools, and again to Dan Bickel for an Arabic parser. Training data there was news text, and the test set was the NIST MT-eval test set. So now I want to say a few things about how we evaluated the accuracy of our system. For those of you who are not familiar with how evaluation is standardly done for machine translation, what you want to do is you want to measure the overlap, degree of overlap between the output of your system and a reference translation. So a first cut, simple way of doing that is to look at a grid consisting of your candidate text and your reference text and place dots in every piece of the grid where you have a word match, and then to find what's called a maximum matching. That is, what is the maximum number of squares in this grid such that no two of them are in the same row or column? Right? This way you don't double count. So this basically counts how many of the words did you get right, but it doesn't say all that much about word order. If you want to measure more about word order, then you might want to give rewards to your system for longer matches, right? Longer spans of words that match. And one way to do that is to find what I call runs, right, of these diagonal hits, right? And you want to reward the runs more than linearly in their length. And a simple way to do that is to give each run a weight that is the area of its minimum enclosing square. Okay? So that's another way of getting a maximum matching that does prefer the matches to be in the right order. And then you normalize. You find the squares that give you the maximum combined area, non-overlapping squares that give you the maximum combined area, take square root to linearize, and then normalize by the length of either the candidate or the reference to get your precision and recall scores. And of course, you can get F measure from those in the usual way. So if we think about the F measure computed this way and what it means, it's roughly speaking the fraction of the grid covered by matches, right? Or once again, the overlap, the degree of overlap between your output and the reference. This is an objective measure that can be automatically computed very quickly. There's, in fact, a tool on the web for doing that, and we have also included this tool in our sandboxes. It's part of our distribution, too. So, OK. Let me say a couple words about speed. We will say something about accuracy. For alignment and training, it's about 1 sentence per second using the setup I described. For translation, it's about 1 sentence a minute. Some optimization yet to do there, but we can translate the NIST MT-eval set in less than a day, so that's good. Now, I mentioned earlier that our work has been very exciting here, and part of the reason for the excitement is that we got results right up to the last minute. I didn't even have time to put them in my slides. So I'll use old-fashioned technology. OK. This is on French-English. And these are training set sizes of, I guess, logarithmic or exponentially increasing size.
You should write it elsewhere, because it's covered by...
Oh, I'm sorry. Yeah, OK, let me write here. In fact, I'm going to use this thing.
It's an airplane. A dog.
A cat.
Sorry, Dan, but could you tilt it just a little more?
Yeah. You have to move to this side of the room.
I know they matter, but.
Okay.
Hold it up after.
Okay, so this is 0, 0.1, 0.2, blah, blah, 0.4, roughly speaking. And okay, so first we have the GTM1 scores, which are usually higher, 0.28, let's see, it's about here, 0.29, 0.33, 0.37, and GTM2. And 0.11, 0.12, 0.12 again, 0.13. Okay. So we run it up to 100,000 sentence pairs of training data. Let me point out that this is already twice the size of the Penn tree bank for people who are with monolingual parsing. I like the trend. This is right. So right. This is F measure. Let's call it with well, I didn't explain exponents, but exponent equals 1. This is again F measure with exponent equals 2. So this is the one that's basically the number of matching words, and this is the extension that takes word order into account. Okay.
And what's the horizontal there? It's
Training set size. Training set size.
In sentences.
In sentences.
Sentences.
And we have
Pardon my
numbers
writing.
For 4-gram matches.
I'm sorry?
4-gram matches.
What about them?
Do we have numbers?
No. Sorry.
So the algorithm
So are you going to show us an example?
An example of the translation?
Yeah.
I
In
don't.
French, I mean, well, I guess it's going to
He
be.
promised a salad for the break.
That's right. Do we actually have an
You
example?
were putting down salad, so.
Oh, that's right. Yeah. Okay. So right in our proposals there are some examples. Yeah. So thanks for the last minute learning curve.
Dan, the evaluation you just described is the lower curve, right? It's exponent 2.
Yeah. So the exponent 2 is the one that uses the enclosing squares. Exponent 1 is the one that just uses the number of hits. And we will have some comparison. One of our students will give some comparisons between our system and an off-the-shelf system of the other kind of statistical MT using these measures so you get some idea of how they correspond. Okay. Okay, so
Is there any reason why you didn't use blue? Because your exponent 2 is not all that different from blue. And
well,
blue
I
would at least give some people an idea of where you are.
okay, well let me first of all say that with respect to any evaluation measure, we're doing badly, right? I mean, these are not good translations. These are much lower than you get with a good SMT system on standard training data sizes. Of course, part of the reason for that is because we only had time to train up to 100,000 sentence pairs. But the other part of the reason is that we have a straw man system. So if you want to see blue scores for the purpose of comparing to papers somewhere else, this is going to be way lower, I can guarantee you that. If you want to know why we didn't use blue score in particular, well, it's this measure precedes blue by about 7 years, and it's objectively better in terms of correlation with human judgments. Okay, so we were going to do this after the break, but how far are we from break?
You can take a break whenever you wish. As long
40
as it's not longer
40
than
minutes
10
from break?
minutes.
Wow. We mistimed it. Well, let's take a break.
You must break, yeah.
Let's take a break. Good. Yeah.